Good morning, everybody. Our presentation is about using prioritization in systematic conservation planning, and it is addressing the conservation of flagship species in the Arabian Gulf, which is the greater flamingo. Just a little of background about the issue is that we are addressing the only breeding population of this species in the Arabian Gulf. So it is migrating species that goes across Asia east to west, but this was found as the only breeding population, and it was very essential for this population and its habitat to be conserved in a highly dynamic environment around the coast of the United Arab Emirates, which is considered one of the fastest developed places in the world. So the declaration of protected areas is considered one of the main strategies for conserving biodiversity. And it is always tackled by development. So conservation and development are considered as two conflicting dynamics. The process of conservation planning is trying to intervene and reduce that conflict by reducing the cost of conservation. The cost would be like the cost for acquiring lands or the cost of offsetting other activities that would have been going if conservation wasn't there. So this process is usually called optimization. It's like prioritizing the areas for conservation with the least cost. So that would be the core of my study here, is how to conserve the species and its habitat while maintaining an optimized cost to the conservation. That's what I previously mentioned, is the capturing the conservation targets with the least cost to the process. So this is the general area where the study is. We found that the flamingo population is in two places, here on the coast, and there is a small wetland here that the flamingo is going back and forth from these two populations. The wetland reserve is already declared as a protected area, so there's no problem about that. But on the coast is being targeted by real estate developers for premium property development. So that's where the issue comes by. We have to set aside this area, and yet we have to deal with all the economical problems that comes with premium high stake activity or economical activity that's also targeting the same area. So the approach that we took, that with all the available conservation data, is to use a method called MarkSAN, which is a prioritization algorithm that uses simulated annealing. It's a term borrowed from metallurgy, where things are brought together in one run, comes out a result, and then everything is dispersed again and brought back into the same process with different conditions. So it's like melting and freezing a metal. That's where the simulated annealing term comes from. In MarkSAN, we have several sources of cost that are assigned to planning units. So the study region is divided into several planning units, and then each planning unit comes with its own scores of conservation features and cost. And within this process, we have a predetermined set of conservation targets. So for instance, if we target to conserve 20% of the habitat, so that's the conservation target, and the algorithm goes into a simulated annealing trying to capture 20% of all the available conservation features in all the planning units with the target of minimizing that cost on each of its elements. So the summation means for all planning units, that's the cost. The PLM or the boundary lengthening is concept comes from reserve design, because a reserve with long edges is much lower or inferior to a reserve with more or less edges. That reduces the edge effect. So the longer the edges of those planning units are exposed to the outside, not to the inside, that increases the boundary cost element. The other one is the SPF, or species penalty factor. It means that whenever a run is not satisfying the conservation feature for a certain conservation target, it comes with a penalty. It becomes penalized. So that's in total increases the score. And the main target of the process is to come with a solution or a profile of planning units that has the lowest score among all the runs. So for fulfilling this process, we had several sources of data about the flamingo species and data about its habitat. For the flamingo, we had data from counts from count stations that are placed along the coast, that's been going for the period of 2009 to 2016. So it's a huge amount of count data, in addition to GPS tracking data that the callers were put on the 10 selected individuals, captured on site, fitted with satellite GPS collars that are solar powered, and data was downloaded from the satellite. Also, we had to calibrate for the PLM, so we used a software called Zona Cognito, which is used to make several runs with a range of PLM values. These PLM values are unitless values. So the Markson run is done for like 100 times with range from 0 to 100. And a curve is created using the score and the PLM value. So we use the one which causes most inflection, that reduces the score, but with the least possible PLM value. So as you see here, this is the king, and this is the flamingo fitted with the satellite collar. Here's a presentation of the data. We have the count data from 2009 to 16, and you see a very obvious trend of declining numbers. That's because of the growing impacts on the tidal coastal area. And here you can see the stations where the counts are made. And this is the track log of the collared flamingos. You can see here there is quite big home range in Abu Dhabi area, which is a protected area, wetland protected area, and along the coast of the study region, which shows the concentration of the population. And we used the kernel home range calculation to come up with these two utilization percentages for the flamingos. And we had a project running for mapping all the marine and terrestrial habitats for Abu Dhabi from satellite imagery. And that was one of the outputs, which is the marine habitat in the study regions that includes elements like tidal floodplains and seagrasses and mangroves, which consist the main foraging and breeding habitat for the flamingo. For the coast elements, the other side of the process, we used the dredging channels because this area is heavily utilized for marine navigation. So if we capture the area as a protected area, we would cause impact as a cost to the marine navigation represented by the dredging channels. And also the other cost element is distance from shoreline. So for the logistics of managing a protected area, in particular, is the distance from coastline, which will pose a lot of logistics for patrolling and managing the area. Collecting all these data elements into the process leaves us with another element of scale. Selecting the size of the planning unit was crucial to the process, so we decided to test with 4 scales or 4 sizes. So we have planning units, hexagonal planning units with 1, 5, 10, and 15 hectares. So we had the algorithm running for these 4 scales, and at the end we compare the results and decide which plan we will get. The last part is of the redefinitions of the process is the conservation targets, and you can see here that there are a little bit ambitious and greedy targets because at the end of the day this will be strict reserve dedicated for the protection of the breeding species. So as you see here, we have the mangroves as 70% and the salt marshes, tidal flats coming next with 50% to be reserved, because these are the main feeding grounds for the flamingo. So they have to be very much captured into whatever solution coming in. So that's the result of the outcome. We have the 4 scales coming with the first one on the top here. This is what we call the best solution, which is suggested to be the boundaries of the reserve. The red planning units are the ones to be contained in the protected area, while the map on the left shows the frequency of selections of each planning unit into each of the 100 runs of the algorithm. So the red planning units on the heat map shows that these are units very important, contained or captured in every single solution of the 100, while the blue ones are never selected. So this is the importance or significance of the planning units. So we can see across the 4 solutions that this one with the 15 hectares and 10 hectares are almost identical to each other, and they are more intricate spatially so that they can be implemented as a protected area boundary. But the 10 hectare solution have scored a higher Mark-Sand score than the 4th one, so it was a very natural decision to select for the 15 hectare solution, which gives us very much intricate, spatially intricate solution to implement as protected area boundary, and also we managed to capture most of the significant planning units into the solution. And it was decided to select the last solution for the delineation of the protected area. And that's the end product, which was selected by the government and adopted and declared as a protected area. Intuitively, you would see that this would have been done before running the whole thing, just looking at the data. But the difference here that it is justifiable, scientifically sound, and reproducible. So whenever any other stakeholder comes and says that this part of the land is very important to the project and we have to get it, it is very justifiable and easy to counteract and say why it was included in the protected area. And that ends my presentation.
We have a few minutes for questions. I have a comment for anyone who wants to try to do this. It's just tricky work, so I, bravo for accomplishing it. One of the tricky things is setting up the data with QGIS. There's QMarkson, so the QMarkson package for QGIS makes it really easy.
It was used here.
So you use QMarkson, okay. Yeah, so that's a really good tool.
Now the same QMarkson is available in ArcMarkson.
Excellent. Yeah, so really good tool. Thank you.
No, I was just going to say that some of the latest satellite imagery with high resolution, you see images from space and you can see the flamingos, right? And I wonder if you can use any of those to enhance your work.
Yeah, and there is a new piece of software called .geese that you can automate the counting of these objects by assigning the animals or bird into classes, and using artificial intelligence, it returns you a count directly from the image.
Cool. Nice.
One more question? Okay, well, thanks so much, Hossameldin.